From the very beginning, Sabrina Pasterski's story does not resemble the familiar arc of prodigy tales shaped by institutions, competitions, or rigid academic pipelines. Instead, it unfolds quietly, driven by an almost stubborn devotion to understanding how things truly work. Born in 1993 in Chicago, she showed an early fascination with mechanics, motion, and the invisible rules governing physical systems. This curiosity was not performative or externally guided. It was deeply internal. She did not seek applause for intelligence, nor validation through grades or titles. What mattered was comprehension. This mindset, rare even among gifted students, would become the defining feature of her intellectual journey. As a teenager, Pasterski undertook a project that would later become symbolic of her character. Rather than merely studying aerodynamics in theory, she built a full-scale, single-engine aircraft in her garage. This was not a school assignment or a staged experiment. It was a personal challenge motivated by a desire to understand flight from the inside out. She studied blueprints, materials, engine mechanics, and safety principles, applying physics not as abstract equations, but as living constraints imposed by reality. When she successfully flew the plane at age 16, the achievement attracted attention, but for Pasterski, the flight itself was not the point. The point was the process of translating theory into physical truth, of testing ideas against the unforgiving logic of nature. This moment revealed something essential about her approach to science. She does not treat knowledge as something to be consumed or accumulated. She treats it as something to be constructed, tested, and sometimes discarded. That approach mirrors the intellectual temperament of the great theoretical physicists of the past, particularly Albert Einstein, who famously relied on thought experiments rather than laboratory machinery to probe the laws of the universe. Pasterski's airplane was not a publicity stunt. It was a physical thought experiment, a way of asking whether her understanding aligned with reality. Her transition into formal physics education did not dilute this independence. At the Massachusetts Institute of Technology, she pursued physics with an intensity that surprised even seasoned professors. While surrounded by peers aiming for prestigious careers or competitive accolades, Pasterski remained singularly focused on fundamental questions. She gravitated toward problems involving symmetry, conservation laws, and the deep structure of spacetime, areas that demand patience and conceptual clarity rather than rapid problem-solving tricks. She was less interested in mastering established techniques than in understanding why those techniques worked at all. What distinguished her during these years was not speed, but depth. She was known for asking questions that cut through layers of assumed knowledge, exposing foundational uncertainties that others overlooked. In classroom discussions, her inquiries often forced a pause, not because they were confusing, but because they were uncomfortably precise. She questioned derivations that were traditionally accepted without scrutiny, and explored the assumptions buried beneath standard models. This habit sometimes made her appear unconventional, even difficult, but it also marked her as someone unwilling to accept authority without understanding. Unlike many young physicists, Pasterski showed little interest in constructing a polished academic identity. She did not aggressively pursue publications, networking, or career signaling. Her focus remained fixed on learning and thinking. This choice set her apart in an academic culture increasingly shaped by metrics, citations, and visibility. To some, this seemed impractical. To others, it was a reminder of an older scientific ethic, one in which ideas mattered more than output. Her move to Harvard for doctoral research further deepened this pattern. There, she began working on some of the most abstract problems in theoretical physics, particularly those involving gravity, quantum mechanics, and spacetime symmetries. These subjects are notoriously difficult, not only mathematically, but conceptually. Progress often requires long periods of uncertainty, during which intuition must be rebuilt from first principles. Pasterski thrived in this environment, not because she had quick answers, but because she was comfortable living with unanswered questions. Her independence extended beyond research topics into her relationship with academic institutions themselves. Unlike most doctoral students, she expressed little concern for traditional milestones or career ladders. She declined prestigious fellowships and avoided tying her work too closely to any single institutional agenda. This decision puzzled many observers, but it reflected a deliberate philosophy. Pasterski has often emphasized that true understanding cannot be rushed or optimized. It requires freedom from external pressures that prioritize productivity over insight. This attitude echoes the early life of Einstein, who developed his revolutionary ideas while working at a patent office, far from academic prestige. In both cases, independence was not a rejection of rigor, but a rejection of conformity. Pasterski's path suggests that she views physics not as a profession, but as a way of seeing the world. Titles, positions, and recognition are secondary to the pursuit of truth. Another defining aspect of her early development is her resistance to overspecialization. Modern science often rewards narrow expertise, but Pasterski has consistently sought connections between disciplines. Her work draws from classical mechanics, quantum field theory, general relativity, and even philosophy of science. This integrative approach allows her to see patterns across domains, particularly in the role of symmetry and conservation laws. Such breadth is increasingly rare, yet historically it has been essential for major breakthroughs. Her early genius, therefore, does not lie in precocious mastery of equations alone. It lies in her ability to maintain intellectual coherence across scales, from mechanical systems to the structure of spacetime itself. She approaches problems with a kind of conceptual humility, acknowledging what is not understood before attempting to build new frameworks. This quality stands in contrast to the confidence-driven culture of modern academia, where uncertainty is often hidden rather than explored. Perhaps most importantly, Pasterski's independent path reflects a deep ethical commitment to science as a human endeavor. She has spoken about the responsibility of physicists to seek truth rather than validation, and to resist turning science into mere technical production. This perspective shapes her early career in subtle but profound ways. She chooses problems that matter conceptually, even if they are unfashionable or slow-moving. She values clarity over complexity, depth over speed. In this sense, her early journey is not just the story of an exceptional individual, but a commentary on the state of modern physics itself. Pasterski represents a reminder that progress does not always come from larger collaborations, faster computers, or more data. Sometimes it comes from a single mind willing to slow down, question assumptions, and follow curiosity wherever it leads. Her independence is not isolation. It is intellectual integrity. As her career continues to unfold, it becomes clear that her early genius cannot be separated from her refusal to be shaped by expectation. She did not follow the path designed for prodigies, nor did she attempt to fit into existing narratives of success. Instead, she built her own trajectory, guided by the same principle that guided her teenage airplane project: understanding must be earned through direct engagement with reality. This principle, simple yet demanding, is what makes her early development so compelling and why many see in her the same quiet revolutionary spirit that once transformed physics forever. As Sabrina Pasterski moved beyond her early formation and into the core of theoretical physics, her work began to reveal a defining theme: an obsession with symmetry as the hidden language of nature. In physics, symmetry is not merely aesthetic balance. It is a deep organizing principle that determines what laws exist and how they behave. Pasterski approached this idea not as a mathematical convenience, but as a philosophical necessity. To her, symmetries are the fingerprints of reality, clues left behind by the universe that hint at its most fundamental structure. Modern physics is built upon symmetries. Conservation of energy, momentum, and charge all arise from underlying symmetrical properties of space and time. Yet, while these ideas are taught early in physics education, their deeper implications are often glossed over. Pasterski's work dives directly into this neglected depth. She became particularly interested in how symmetries behave at the boundaries of spacetime, places where conventional intuition breaks down. These include regions infinitely far away, near black holes, or at the edge of causal horizons. It is in these extreme settings that the universe reveals its most subtle secrets. One of her most influential contributions involves asymptotic symmetries, a concept describing how physical laws behave at infinity. For decades, these symmetries were considered mathematical curiosities with little physical meaning. Pasterski challenged this assumption. She showed that these symmetries are not abstract leftovers, but active players that govern how particles, fields, and information interact across spacetime. Her work suggested that the edges of the universe are not empty or irrelevant, but structured and informative. This insight had immediate consequences for how physicists think about gravity. General relativity describes gravity as the curvature of spacetime, but it struggles to reconcile with quantum mechanics. Pasterski's research sits precisely at this intersection. By studying symmetries that persist even in gravitational systems, she helped reveal hidden conservation laws that survive in regimes where traditional laws appear to fail. These ideas imply that gravity may be less chaotic and more orderly at a fundamental level than previously believed. Her approach stood out because she did not treat equations as final answers. She treated them as questions. When standard formulations produced infinities, ambiguities, or paradoxes, she did not accept these as technical annoyances. Instead, she interpreted them as signs that something deeper was being overlooked. In particular, she focused on how particles scatter and exchange information in gravitational fields, examining the symmetries that remain intact during these interactions. This work connected quantum field theory with gravitational dynamics in a way that felt natural rather than forced. A striking feature of her research is its conceptual economy. Pasterski often uses minimal assumptions to extract maximal insight. Rather than constructing elaborate theoretical frameworks, she searches for universal principles that must hold regardless of specific models. Symmetry plays this role perfectly. It does not depend on the details of particles or forces, only on the structure of spacetime itself. By grounding her work in symmetry, she avoids speculative excess and remains anchored to physical necessity. Her contributions also reshaped how physicists understand soft particles, low-energy excitations that were once considered negligible. Pasterski demonstrated that these soft particles are intimately connected to asymptotic symmetries and carry physical information across vast distances. This realization transformed what was previously regarded as background noise into a meaningful signal. It suggested that information is distributed throughout space-time more delicately than previously thought, woven into the very fabric of physical interactions. This perspective had profound implications for the black hole information problem, one of the most stubborn puzzles in theoretical physics. According to classical reasoning, information falling into a black hole should be lost forever, violating the principles of quantum mechanics. Pasterski's work contributed to a growing body of evidence that information is not destroyed, but encoded in subtle correlations governed by symmetry. While she did not claim to solve the paradox outright, her insights helped shift the conversation from despair to possibility. What makes her breakthrough work especially remarkable is its clarity. Many papers in high-level theoretical physics are technically impressive but conceptually opaque. Pasterski's writing, by contrast, strives for transparency. She carefully explains why a symmetry matters, what physical role it plays, and how it reshapes our understanding. This clarity has made her work influential beyond her immediate field, attracting attention from physicists working on quantum gravity, particle physics, and even cosmology. Her collaborations reflect this breadth. She has worked with some of the most respected figures in modern theoretical physics, yet she maintains a distinctive voice within these collaborations. She does not simply extend existing ideas, she reframes them. Colleagues often note that her contributions change how a problem is perceived, not just how it is calculated. This ability to shift perspective is a hallmark of genuine theoretical innovation. Equally important is her resistance to fashionable trends. Theoretical physics often moves in waves, with certain frameworks dominating attention for years at a time. Pasterski has shown little interest in aligning herself with any single trend. Instead, she follows questions that persist regardless of fashion. Symmetry, after all, does not go out of style. It remains relevant as long as the universe exists. This timeless focus gives her work a durability that many contemporary theories lack. Her breakthroughs also challenge the division between classical and quantum physics. By revealing how classical gravitational symmetries manifest in quantum processes, she helps bridge a conceptual gap that has long frustrated physicists. This does not mean she proposes a final theory of quantum gravity, but it does mean she illuminates a path forward. Her work suggests that the reconciliation of these frameworks may emerge not from radical new entities, but from a deeper understanding of existing principles. There is also a philosophical dimension to her work that cannot be ignored. Symmetry is closely related to the idea of equivalence, the notion that different perspectives can reveal the same underlying truth. Pasterski's research embodies this idea. She shows that phenomena appearing different at first glance may be unified through symmetry. This unifying vision resonates with the deepest aspirations of physics, to reveal simplicity beneath complexity. As her ideas circulated through the scientific community, they influenced not only research directions, but also how young physicists think about foundational problems. Her work serves as a reminder that progress does not always require new particles or extra dimensions. Sometimes it requires listening more carefully to what established theories are already trying to tell us. Symmetry, in this sense, becomes a conversation between mathematics and reality, one that Pasterski has learned to hear with unusual sensitivity. In examining her breakthrough work, it becomes clear that her contribution is not a single result, but a way of thinking. She treats symmetry as a guiding principle, a compass rather than a destination. This mindset allows her to navigate the most abstract regions of physics without losing contact with physical meaning. It also explains why her work feels both modern and classical at the same time, rooted in contemporary mathematics, yet inspired by the conceptual clarity of earlier giants. As this phase of her career unfolds, her focus on symmetry continues to open doors rather than close them. Each insight reveals further questions, deeper structures, and new connections. Rather than offering closure, her work expands the landscape of possibility. This is perhaps the strongest sign of a genuine breakthrough. It does not end inquiry, but renews it. And in that renewal, Sabrina Pasterski's contribution to theoretical physics stands as one of the most intellectually fertile developments of her generation. As Sabrina Pasterski's work matured, it naturally moved toward one of the most difficult and mysterious frontiers in all of science, the relationship between quantum mechanics and gravity. This is the domain where our best theories stop speaking clearly to one another, where spacetime itself becomes unstable under inquiry, and where black holes emerge not just as astronomical objects, but as conceptual fault lines in human understanding. Pasterski entered this territory not with the ambition of conquering it, but with the patience to listen to what its contradictions were trying to reveal. Quantum gravity is not a single theory but a problem, perhaps the deepest problem in modern physics. Quantum mechanics governs the microscopic world with extraordinary accuracy, while general relativity describes gravity and spacetime on cosmic scales. Yet when these two frameworks are pushed into the same regime, such as inside black holes or at the origin of the universe, they resist unification. Pasterski's contribution lies not in proposing a grand unifying formula, but in clarifying how these frameworks already interact in subtle, often overlooked ways. Black holes became a central focus of her work because they represent the point where gravity becomes extreme and quantum effects cannot be ignored. Traditionally, black holes were viewed as simple objects defined by mass, charge, and spin. Everything else, according to classical reasoning, vanished beyond the event horizon. This idea, often summarized as black holes have no hair, implied that information about matter falling into a black hole was lost forever. Such loss violates a core principle of quantum mechanics, which insists that information is conserved. Rather than approaching this paradox with speculative assumptions, Pasterski examined the mathematical structure of spacetime near black holes with extraordinary care. She focused on the symmetries that survive even in these extreme environments. What she found, along with collaborators, was that black holes may not be as simple as once believed. They may carry subtle imprints of information encoded in gravitational fields at their boundaries. These imprints do not appear as classical features, but as delicate quantum correlations governed by symmetry. This insight reframed the black hole information problem. Instead of asking where information goes, Pasterski's work suggested that information may never truly leave the system. It may be redistributed in ways that are difficult to detect but fundamentally preserved. This does not trivialize the paradox, but it shifts its meaning. The problem becomes not one of destruction, but of decoding. Information is not gone, it is hidden in plain sight, woven into the geometry of spacetime itself. Her work emphasized the role of horizons, the invisible boundaries that define black holes. Horizons are not physical surfaces, yet they have measurable effects. They determine what observers can see and influence how energy and information flow. Pasterski treated horizons not as passive limits, but as dynamic regions rich with structure. By studying how quantum fields behave near these boundaries, She helped reveal that horizons possess degrees of freedom previously ignored or misunderstood. One of the most radical implications of this approach is the idea that spacetime itself may store information in a distributed way. Instead of being an empty stage on which physics plays out, spacetime becomes an active participant. Pasterski's research supports the view that geometry and information are deeply intertwined. This perspective resonates with emerging ideas in theoretical physics, suggesting that spacetime may arise from more fundamental informational principles. Her contributions also extended to the study of gravitational scattering, the process by which particles interact through gravity at high energies. These interactions are notoriously difficult to analyze, yet they offer crucial clues about quantum gravity. Pasterski demonstrated that even in such violent processes, certain symmetrical patterns persist. These patterns act as anchors, preserving consistency between quantum mechanics and gravity. They suggest that beneath apparent chaos, the universe obeys a deeper order. What distinguishes Pasterski's work in this area is its restraint. She avoids dramatic claims and resists overselling implications. Instead, she carefully builds arguments from established principles, showing how new insights emerge naturally when those principles are applied with sufficient rigor. This approach has earned her respect among physicists who value precision over speculation. It also gives her ideas staying power in a field where many proposals fade quickly. Her research contributed to a broader shift in how black holes are understood. Once viewed as theoretical curiosities, black holes are now central to debates about the nature of reality itself. Pasterski's work helped legitimize the idea that black holes are laboratories for quantum gravity, not obstacles to it. By revealing that information conservation may survive even under extreme gravitational collapse, she strengthened the case for a consistent underlying theory. There is also a human dimension to this work that is often overlooked. Black hole physics confronts us with limits of observation, limits of language, limits of intuition. Pasterski's willingness to engage with these limits reflects a deeper intellectual courage. She does not shy away from uncertainty. Instead, she treats it as a guide, signaling where understanding must grow. This attitude echoes the spirit of earlier physicists who embraced paradox as a path to discovery. Her contributions influenced ongoing discussions about holography, the idea that information in a volume of space can be described by data on its boundary. While she does not frame her work within a single theoretical program, her results align naturally with holographic thinking. They suggest that boundaries are not secondary features, but fundamental elements of physical reality. In black holes, the boundary becomes the key to preserving consistency between gravity and quantum mechanics. Pasterski's work also has implications for cosmology, the study of the universe as a whole. If information is preserved at horizons, similar principles may apply to cosmic horizons associated with the expansion of the universe. This raises profound questions about the origin of structure, the arrow of time, and the fate of information on cosmological scales. While these questions remain open, her research provides tools for approaching them without abandoning established physics. What makes these contributions especially significant is their conceptual clarity. Quantum gravity is often portrayed as hopelessly abstract, accessible only through complex mathematics. Pasterski's work shows that clarity is possible even in this domain. By grounding her analysis in symmetry, conservation, and physical intuition, she makes progress without obscuring meaning. This clarity does not simplify the problem, but it makes it navigable. her influence extends beyond specific results to the culture of theoretical physics itself. She represents a mode of inquiry that values patience over productivity and understanding over novelty. In a field driven by competition and rapid publication, this stance is quietly radical. It suggests that the deepest problems cannot be rushed, and that progress may require a return to first principles. As this phase of her work continues, it becomes clear that her contributions to quantum gravity and black hole physics are not isolated achievements. They form part of a coherent vision in which the universe is governed by principles that remain consistent even under extreme conditions. This vision does not promise easy answers, but it restores confidence that the laws of nature do not break down simply because they are difficult to understand. In this sense, Pasterski's work offers something rare, not a solution, but a direction. It suggests that the path to quantum gravity may lie not in inventing new realities, but in more deeply understanding the one we already inhabit. Black holes, once symbols of destruction and loss, become symbols of continuity and hidden order. Through her careful, disciplined inquiry, Sabrina Pasterski helps transform our most troubling cosmic mysteries into opportunities for deeper insight. This is why her contributions to black hole physics matter far beyond the equations themselves. They reshape how physicists think about information, space-time, and the unity of nature's laws. They remind us that even in the darkest regions of the universe, understanding is not extinguished. It waits, encoded in symmetry and structure, for minds patient enough to uncover it. Recognition in science does not always arrive with applause or headlines. Sometimes it appears quietly, in the form of attention from those who rarely give it lightly. In the case of Sabrina Pasterski, recognition has emerged not through public self-promotion, but through the sustained interest and respect of some of the most influential physicists in the world. This kind of recognition is subtle, but it is also the most meaningful, because it reflects judgment based on ideas rather than image. From early in her research career, Pasterski's work began circulating among elite theoretical physics circles. Her papers were read carefully, not skimmed. They were discussed in seminars where the audience was known for skepticism and intellectual rigor. In these environments, praise is rare and criticism is sharp. Yet her ideas repeatedly survived scrutiny. Senior physicists recognized that her work was not incremental, not merely an extension of existing frameworks, but something that reshaped how familiar problems were being approached. What drew attention first was not her age or background, but the unusual clarity of her thinking. Many established physicists noted that her arguments cut through layers of technical complexity to reveal underlying structure. This ability is especially valued in theoretical physics, where it is easy to hide confusion behind mathematics. Pasterski's work did the opposite. It exposed assumptions, identified symmetries others had overlooked, and reframed problems in ways that felt both original and inevitable. Nobel laureates and leading figures in quantum field theory and gravity began to reference her work, not as a curiosity, but as a foundation. Her name appeared in discussions about the future of quantum gravity and black hole physics, fields dominated by decades of unresolved debate. This kind of acknowledgement is not ceremonial. It signals that an idea has entered the shared intellectual landscape and cannot be ignored. One of the most striking aspects of her recognition is how it transcends subfields. Physicists working in particle theory, gravitational physics, and mathematical physics have all engaged with her ideas. This is unusual in a discipline that has become increasingly fragmented. Her work functions as a bridge, connecting communities that often speak different technical languages. When ideas travel this widely, it is a sign that they address something fundamental rather than specialized. Equally significant is the way senior scientists describe her contributions. They often emphasize not just what she has done, but how she thinks. She is frequently praised for intellectual honesty, for asking questions that others avoid, and for resisting premature conclusions. These qualities are not easily measured, but they are deeply respected. In private conversations and public lectures alike, her name is often mentioned with a tone of seriousness that reflects trust in her judgment. Recognition has also come through invitations rather than awards. She has been invited to speak at high-level workshops and closed-door conferences where participation is limited to researchers shaping the direction of the field. These invitations are extended not to rising stars, but to minds whose input is considered essential. Her presence in such spaces indicates that her peers see her not as a student of ideas, but as a contributor to them. What makes this recognition especially compelling is that Pasterski has never sought it. She has declined high-profile fellowships and avoided aligning herself with institutional prestige. In a culture where visibility often determines opportunity, her approach is almost anomalous. Yet recognition has followed her regardless, suggesting that substance still matters, at least in the deepest layers of scientific discourse. Her relationship with mentors and collaborators further illustrates this point. She has worked alongside some of the most respected names in physics, not as a subordinate voice, but as an intellectual equal. Colleagues have noted that discussions with her often feel less like instruction and more like mutual exploration. This dynamic is rare, especially given the hierarchical nature of academia. It reflects recognition not just of talent, but of authority earned through insight. There is also an intergenerational dimension to her recognition. Younger physicists often cite her as a model for how to engage with foundational problems without sacrificing integrity. Older physicists see in her a reminder of an earlier era, when theoretical physics was driven more by conceptual daring than by institutional momentum. In this way, her recognition bridges generations, uniting different visions of what physics can and should be. The media's occasional comparison of Pasterski to Einstein has been met with caution within the scientific community, yet it has not been dismissed outright. This is telling. Physicists are notoriously resistant to grand comparisons, especially to figures of historical magnitude. That such comparisons are even entertained reflects the unusual nature of her impact. It is not that she is expected to replicate Einstein's achievements, but that she embodies a similar independence of thought and commitment to first principles. Recognition has also come through silence, an often overlooked indicator in science. Her ideas have not been quickly overturned or absorbed into obscurity. Instead, they persist, continuing to influence research years after publication. In theoretical physics, where fashions change rapidly, persistence is a mark of significance. It suggests that her work addresses questions that remain unresolved, questions that others must still grapple with. Another dimension of her recognition lies in how her work is taught and discussed. Concepts she has clarified are increasingly appearing in advanced lectures and graduate-level discussions. When ideas become part of education, they gain a kind of permanence. They shape how future physicists think, not just what they know. This quiet integration into the intellectual fabric of the field is one of the most enduring forms of recognition. Her recognition is also shaped by what she refuses to do. She does not simplify her ideas for popularity, nor does she frame her work in sensational terms. This restraint earns trust. Physicists recognize when someone is committed to understanding rather than persuasion. In an era where science communication sometimes blurs into performance, her seriousness stands out. There is an ethical dimension to this respect as well. Pasterski has spoken about the responsibility of physicists to prioritize truth over career advancement. This perspective resonates with senior scientists who have seen how incentives can distort research priorities. Her choices reflect a belief that science is a collective endeavor with long-term consequences, not a competition for short-term recognition. This ethical clarity strengthens the credibility of her work. International recognition further underscores her influence. Her ideas are discussed in research groups across Europe, North America, and Asia. This global engagement indicates that her work speaks to universal problems, not regionally defined research agendas. Physics, at its best, transcends borders, and her recognition reflects this ideal. Despite all this, Pasterski remains an enigmatic figure. She rarely gives interviews and avoids cultivating a public persona. This has only intensified curiosity around her work. In science, mystery often surrounds those who let their ideas speak louder than their presence. Her recognition grows not through repetition of her name, but through continued engagement with her ideas. What emerges from this pattern is a portrait of recognition grounded in substance rather than spectacle. It is recognition earned slowly, through consistency, clarity, and courage. Leading physicists recognize in Pasterski not just a talented researcher, but a guardian of scientific values that feel increasingly fragile. Her work reminds them of why they entered the field in the first place. In this sense, recognition becomes more than personal validation. It becomes a signal to the scientific community about what kind of work matters. Pasterski's recognition suggests that depth still outweighs speed, that understanding still outweighs output, and that integrity still commands respect. These messages are as important as her technical contributions. As her career continues, this recognition is likely to evolve, but its foundation is already clear. It is built not on predictions or promises, but on demonstrated insight. It reflects a consensus among those best equipped to judge that her work has altered the intellectual landscape of modern physics. Ultimately, the recognition Sabrina Pasterski has received tells a story not just about her, but about science itself. It shows that even in a complex, competitive, and institutionalized world, a single mind committed to understanding can still be heard. And when it is heard by those who shape the future of physics, that recognition carries a weight no headline can match. The comparison between Sabrina Pasterski and Albert Einstein did not emerge from media hype alone, nor was it created as a symbolic gesture to crown a new scientific icon. It arose slowly, organically, within the private conversations of physicists who sensed a familiar pattern in her way of thinking. Einstein's legacy is not defined solely by relativity or famous equations, but by a particular intellectual temperament, an insistence on first principles, a resistance to authority without understanding, and a deep trust in conceptual clarity over formal complexity. It is this temperament, more than any single discovery, that has led many to see echoes of Einstein in Pasterski's work. Einstein revolutionized physics not by mastering existing frameworks faster than others, but by questioning the assumptions everyone else accepted without hesitation. As a young man, he asked why time should be absolute, why simultaneity should be universal, and why space should exist independently of observers. These were not technical questions, they were conceptual ruptures. Pasterski's work reflects a similar instinct. She is drawn not to well-polished theories, but to the seams where ideas fail to align. Her questions often begin where textbooks stop, at the point where explanation gives way to habit. One of the strongest parallels lies in her relationship with mathematics. Einstein famously used mathematics as a tool rather than a guide. He relied first on physical intuition, using equations to formalize insights rather than to generate them. Pasterski shares this approach. While she possesses formidable mathematical skill, she does not allow formalism to substitute for understanding. Her papers reveal a careful balance between rigor and intuition, with equations serving as expressions of ideas rather than barriers to them. This style stands in contrast to much of modern theoretical physics, where mathematical complexity is often mistaken for depth. Another reason for the comparison lies in her independence from institutional incentives. Einstein developed his most important ideas while working outside academia, free from its pressures and expectations. Pasterski, despite operating within elite institutions, has consciously distanced herself from the careerism that dominates modern science. She has declined prestigious fellowships, avoided aggressive publication strategies, and resisted the urge to brand herself. This detachment mirrors Einstein's indifference to professional advancement during his formative years. In both cases, the work came first, and recognition followed reluctantly. There is also a shared skepticism toward authority. Einstein famously challenged the greatest physicists of his time, not out of arrogance, but out of fidelity to logic. Pasterski demonstrates a similar willingness to question established figures and frameworks when they conflict with first principles. She does not reject tradition lightly, but she refuses to treat it as final. This balance between respect and independence is rare, especially in a hierarchical academic culture. It requires confidence rooted not in ego, but in understanding. The Einstein comparison is further reinforced by Pasterski's focus on universality. Einstein sought laws that applied everywhere, regardless of frame or scale. His theories were powerful because they were inevitable once their premises were accepted. Pasterski's work exhibits the same drive. Her focus on symmetry is not decorative. It is a search for principles that must hold under all circumstances. Symmetry, like relativity, strips away accidental features and exposes what cannot be otherwise. This pursuit of inevitability is a hallmark of foundational physics. Both thinkers also share a remarkable patience with unresolved questions. Einstein spent decades wrestling with the unification of gravity and electromagnetism, long after others had moved on. Pasterski demonstrates a similar willingness to remain with difficult problems without forcing premature solutions. She does not treat unanswered questions as failures, but as signs that understanding has not yet reached its proper depth. This patience is increasingly rare in a research culture driven by rapid results. The comparison also reflects a shared clarity of expression. Einstein was a gifted communicator, capable of explaining complex ideas without distortion. Pasterski's writing shows the same respect for the reader. She does not rely on obscurity to convey authority. Instead, she works to make her arguments transparent, even when dealing with abstract concepts like asymptotic symmetries or black hole horizons. This clarity is not simplification, it is discipline. It reflects a belief that if an idea cannot be explained clearly, it may not yet be fully understood. Another parallel lies in their attitude toward mystery. Einstein famously resisted interpretations of quantum mechanics that abandoned realism, yet he never dismissed the theory's success. He lived with tension between belief and evidence. Pasterski inhabits a similar tension in modern physics. She works at the boundary between quantum mechanics and gravity, fully aware that existing frameworks are incomplete. Rather than choosing sides in theoretical debates, she explores the space between them, looking for principles that transcend current divisions. The cultural context also strengthens the comparison. Einstein emerged during a period when physics faced a conceptual crisis. Classical mechanics could not explain electromagnetic phenomena, and new ideas were desperately needed. Today's physics faces a similar crisis in the failure to reconcile quantum mechanics with gravity. Pasterski's work addresses this crisis directly, not by proposing radical new entities, but by re-examining the foundations of existing theories. This parallel historical position makes the comparison feel less metaphorical and more structural. It is important to note that physicists themselves approach the Einstein comparison cautiously. They understand the danger of mythologizing living scientists, yet the fact that the comparison persists suggests that it fulfills a genuine need. It is not a prediction of identical achievement, but an acknowledgement of a shared approach to inquiry. Pasterski represents a style of physics that many fear is disappearing, slow, principled, and conceptually driven. There is also an ethical resonance in the comparison. Einstein saw science as a moral endeavor, believing that understanding the universe carried responsibilities toward humanity. Pasterski has expressed similar concerns about the direction of modern science, warning against the commodification of research and the erosion of intellectual integrity. This ethical dimension deepens the comparison, linking not just intellects, but values. The comparison is also fueled by what Pasterski does not do. She does not chase publicity, does not cultivate controversy, and does not frame her work as revolutionary rhetoric. Einstein, too, was famously indifferent to fame once it arrived. In both cases, restraint amplifies credibility. When praise is not sought, it carries more weight when it comes. Critically, the Einstein comparison does not imply inevitability. Einstein himself was shaped by historical circumstances that cannot be replicated. Pasterski operates in a vastly different scientific ecosystem, with larger collaborations, more complex mathematics, and stronger institutional pressures. Yet the persistence of the comparison suggests that despite these differences, certain intellectual qualities remain timeless. Curiosity, independence, clarity, and courage do not belong to any era. The comparison also functions as a mirror for the scientific community. By invoking Einstein, physicists are implicitly asking what kind of science they value. Pasterski's work suggests that even today, depth still matters more than volume, and understanding more than productivity. In this sense, the comparison is less about her future achievements and more about what her presence reveals about the field. As her career unfolds, the Einstein comparison will likely evolve, perhaps fade, perhaps deepen, but at this stage, it serves as a meaningful signal rather than a verdict. It highlights a rare convergence of traits that do not often appear together in modern science. It draws attention to a mind operating at the foundations rather than the surface. Ultimately, Sabrina Pasterski is not important because she resembles Einstein. She is important because she embodies the same commitment to truth that made Einstein transformative. The comparison endures not because history is repeating itself, but because certain ways of thinking remain essential whenever humanity confronts the limits of understanding. In that sense, The comparison tells us as much about the enduring spirit of physics as it does about the individual who has inspired it. Sabrina Pasterski's approach to learning and research stands apart not because it rejects tradition outright, but because it quietly refuses to be governed by it. From the outside, her path may appear unconventional, even puzzling, yet from within it follows a rigorous internal logic rooted in curiosity, discipline, and intellectual honesty. She does not treat education as a ladder to be climbed or research as a product to be delivered. Instead, she approaches both as processes of alignment, a way of bringing thought into closer contact with reality. In most academic environments, learning is structured around milestones. Courses must be completed, exams passed, papers published, grants secured. Progress is measured externally through credentials and output. Pasterski's relationship with learning operates differently. She does not move forward to satisfy requirements. She moves forward only when understanding feels complete enough to support the next question. This creates a rhythm that often clashes with institutional timelines, but it also produces depth that cannot be rushed. Her early habits already reflected this orientation. Rather than memorizing formulas, she sought to reconstruct them from first principles. She treated established results not as conclusions, but as checkpoints, asking why they had to be true and under what conditions they might fail. This habit slowed her down in conventional settings, but it sharpened her intuition. Over time, this intuition became her primary guide, allowing her to navigate complex theories without losing conceptual footing. Pasterski's unconventional learning style is characterized by selective intensity. She does not attempt to absorb everything. Instead, she focuses deeply on a small number of foundational ideas until they become transparent. Once clarity is achieved, she moves outward, connecting those ideas to broader frameworks. This contrasts with the common academic strategy of breadth, first exposure, where familiarity is mistaken for understanding. Her method prioritizes coherence over coverage. In research, this philosophy manifests as patience. She is willing to sit with a problem for extended periods, resisting the temptation to publish partial insights. In a culture where speed is rewarded, this patience can appear counterproductive, yet it allows her to identify connections that only emerge when ideas are given time to mature. Many of her insights arise not from sudden inspiration, but from sustained attention, from returning to the same question repeatedly until it reveals something new. Another defining feature of her approach is her resistance to overspecialization. While modern physics encourages narrow focus, Pasterski deliberately maintains a broad conceptual range. She moves comfortably between classical mechanics, quantum field theory, general relativity, and the philosophy underlying these disciplines. This breadth is not superficial. It allows her to recognize when problems framed as technical difficulties are actually conceptual mismatches between theories. Her learning process is also deeply dialogical, but not in the usual sense of collaboration. She treats texts, equations, and physical principles as interlocutors. When a derivation feels forced or a result appears arbitrary, she pauses, not to accept it, but to interrogate it. This internal dialogue continues until the idea either becomes clear or reveals its limitations. In this way, confusion is not avoided but used as a diagnostic tool. Pasterski's unconventional approach extends to her use of mentorship. Rather than seeking validation or direction, she seeks challenge. She values mentors who question her assumptions and push her to articulate her reasoning with precision. This relationship is not hierarchical but reciprocal. She engages with mentors as fellow thinkers, not as authorities to be followed. This dynamic accelerates growth, but it also demands confidence rooted in understanding rather than status. Her research habits reflect a similar independence. She does not align herself with dominant theoretical programs simply because they are popular. Instead, she evaluates ideas based on their explanatory power and conceptual necessity. This has led her to work on problems that others consider unfashionable or too difficult to yield quick results. Yet these are often the problems that lie at the heart of unresolved tensions in physics. One of the most striking aspects of her approach is her comfort with incompleteness. She does not feel compelled to resolve every question immediately. Instead, she allows gaps in understanding to remain visible. This openness to uncertainty contrasts sharply with the performative confidence often expected in academic settings. Yet it is precisely this openness that enables genuine progress. By acknowledging what is not known, she creates space for deeper insight. Pasterski also resists the compartmentalization of learning and research. For her, learning does not end when formal education does, and research does not begin only after credentials are earned. Both are continuous processes. She continues to study foundational material long after it would be considered unnecessary, revisiting classical papers and historical debates to refine her perspective. This recursive learning strengthens her research, grounding new ideas in a deep understanding of old ones. Her unconventionality is also evident in how she relates to productivity. She does not equate value with quantity. A single clear idea, carefully articulated, holds more significance for her than multiple incremental results. This attitude runs counter to prevailing incentive structures, yet it aligns with the historical reality of major scientific breakthroughs, which often emerged from prolonged periods of quiet reflection rather than constant output. Technology, too, plays a different role in her work. While she is fully capable of using advanced computational tools, she does not rely on them as substitutes for understanding. She prefers analytic reasoning and conceptual models, using computation only when it serves clarity. This preference reflects a belief that tools should extend thought, not replace it. There is also an ethical dimension to her approach. Pasterski views learning and research as responsibilities rather than competitions. She is wary of framing science as a race, fearing that speed and visibility can distort priorities. This ethical stance influences her choices, from the problems she pursues to the way she presents her work. She avoids sensationalism, choosing accuracy and nuance even when they make ideas harder to communicate. Her unconventional approach has, at times, created friction within traditional academic structures. Expectations about timelines, publication frequency, and career progression do not always align with her rhythm. Yet rather than adjusting her approach to fit these structures, she adapts the structures around her, carving out intellectual space through consistency and clarity. Over time, this earns respect, even from those who initially question her methods. This approach also shapes how others learn from her. Students and colleagues who engage with her work often report a shift in their own thinking. They become more attentive to assumptions, more patient with complexity, and more willing to question established narratives. In this way, her influence extends beyond specific research contributions to the culture of learning itself. Her unconventional path does not reject rigor, it demands more of it. By refusing shortcuts, she raises the standard for what it means to understand something fully. This rigor is internal rather than enforced. It comes from a personal commitment to coherence and truth, not from fear of evaluation. As her career progresses, this approach positions her uniquely within physics. She is neither an outsider nor a conventional insider. She participates fully in the discipline while quietly redefining its norms. Her work demonstrates that it is possible to engage deeply with modern science without surrendering intellectual independence. Ultimately, Sabrina Pasterski's unconventional approach to learning and research is not a strategy but a reflection of character. It arises from a belief that understanding is valuable in itself, independent of recognition or reward. This belief shapes every aspect of her work, from how she studies to how she contributes. In a scientific culture often dominated by urgency, her approach is a reminder of the power of patience. It suggests that the deepest insights do not come from moving faster, but from seeing more clearly. And in this clarity, achieved through an unconventional yet deeply principled path, lies one of the most compelling aspects of her contribution to modern physics: the impact of Sabrina Pasterski on the future of fundamental physics cannot be measured solely by citations, institutional roles, or immediate technological applications. Her influence operates at a deeper level, shaping how physicists think about problems that remain unresolved and how they approach the very idea of understanding nature. In a field facing conceptual stagnation despite immense technical sophistication, her work represents a quiet but powerful shift in direction. Modern physics stands at a crossroads. Its mathematical tools have never been more advanced, yet its foundational questions remain stubbornly unanswered. The unification of quantum mechanics and gravity, the nature of spacetime, the meaning of information, and the limits of physical law continue to resist closure. Pasterski's impact lies in how she reframes these questions, not as failures of imagination, but as invitations to revisit first principles with greater care. One of the most significant ways her work shapes the future is by restoring confidence in foundational inquiry. For decades, much of theoretical physics has been driven by speculative frameworks that extend beyond experimental reach. While mathematically impressive, many of these approaches struggle to make contact with physical reality. Pasterski's research suggests a different path forward, one grounded in symmetry, conservation, and internal consistency. This approach does not abandon ambition, but it redirects it toward questions that can be answered through conceptual clarity rather than conjecture. Her emphasis on symmetry as a guiding principle has long-term consequences for how new theories may be constructed. Symmetry has historically played a central role in major breakthroughs, from classical mechanics to quantum field theory. By revealing how deep symmetries operate even in gravitational and quantum regimes, Pasterski strengthens the idea that the future of physics may depend less on discovering new entities and more on understanding existing structures more fully. This perspective encourages restraint and discipline, qualities often overshadowed by the allure of novelty. Another aspect of her impact is methodological. She demonstrates that progress in fundamental physics does not require abandoning rigor for creativity or intuition for mathematics. Instead, it requires a careful balance of both. Her work models a way of thinking in which intuition guides inquiry, mathematics formalizes insight, and physical meaning remains central. This model is especially influential for younger physicists navigating a landscape crowded with competing approaches. Her influence also extends to how physicists think about information. Traditionally treated as an abstract quantity, information is increasingly viewed as a fundamental component of physical reality. Pasterski's work contributes to this shift by showing how information is preserved and structured even in extreme gravitational environments. This insight has implications far beyond black holes. It affects how physicists understand entropy, time, causality, and the emergence of spacetime itself. In the future, theories of quantum gravity may rely less on dramatic departures from known physics and more on subtle reinterpretations of existing laws. Pasterski's research supports this trajectory. By demonstrating that consistency between quantum mechanics and gravity may already be encoded in their shared symmetries, she provides a framework for incremental yet profound progress. This approach reduces the risk of building theories detached from reality, a concern increasingly voiced within the physics community. Her impact is also cultural. Physics, like all human endeavors, is shaped by incentives. Speed, visibility, and productivity often dominate evaluation. Pasterski's career challenges these values by showing that influence can arise without conformity to these metrics. Her success without aggressive self-promotion sends a powerful message to future generations. Depth and integrity still matter. This message may prove as influential as any specific result. As her ideas circulate, they encourage physicists to slow down and reflect. They promote a culture in which asking better questions is valued over producing faster answers. This shift is subtle, but it has long-term consequences. Fields evolve not only through discoveries, but through changes in what practitioners consider important. Pasterski's work nudges the field toward valuing coherence, clarity, and patience. Her impact on future physics also lies in her resistance to fragmentation. As specialization deepens, communication across subfields becomes more difficult. Pasterski's integrative approach demonstrates that foundational principles can bridge these divides. Her work connects quantum field theory, general relativity, and information theory in a way that feels natural rather than forced. This integrative vision may guide future efforts to unify disparate areas of physics. There is also an educational dimension to her influence. As her ideas become part of advanced discussions and curricula, they shape how future physicists are trained. Students exposed to her work learn to question assumptions, to value symmetry, and to prioritize conceptual understanding. This educational impact may outlast specific theories, shaping the intellectual habits of an entire generation. Her influence extends beyond physics itself. Fundamental physics has always shaped broader philosophical views about reality, causality, and determinism. By emphasizing consistency and information preservation, Pasterski's work contributes to ongoing philosophical debates about the nature of existence. These ideas influence not only scientists, but also thinkers in philosophy, mathematics, and even computer science. Importantly, her impact does not depend on delivering a final theory. Physics advances through partial insights that clarify what is possible and what is not. Pasterski's work narrows the space of viable theories by revealing constraints imposed by symmetry and consistency. This narrowing is a form of progress, even in the absence of definitive answers. It guides future research away from dead ends and toward fertile ground. Her presence also alters expectations about leadership in science. She does not lead through authority or charisma, but through example. Her commitment to understanding sets a standard that others aspire to meet. This form of leadership is quiet but enduring. It reshapes norms rather than enforcing them. As physics confronts its next century of challenges, voices like Pasterski's may become increasingly important. The problems ahead are not merely technical, they are conceptual. They require thinkers willing to question deeply, to tolerate uncertainty, and to resist easy narratives. Her work embodies these qualities, positioning her as a guiding influence even as specific debates evolve. The future of fundamental physics will likely be shaped by those who can hold complexity without losing clarity. Pasterski's impact lies precisely here. She shows that clarity is not the enemy of depth, but its prerequisite. By insisting on understanding before expansion, she offers a path forward that is both ambitious and grounded. In the long view, her influence may be felt not through a single revolutionary moment, but through a gradual transformation of how physics is practiced. The questions physicists ask, the methods they trust, and the values they uphold will all bear traces of this influence. Such impact is difficult to quantify, but it is the kind that endures. Ultimately, Sabrina Pasterski's impact on the future of fundamental physics lies in restoring faith in the idea that the universe is intelligible, not because it yields easily, but because it obeys principles worth uncovering. Her work suggests that even in the face of profound mystery, understanding is not beyond reach. It requires patience, humility, and courage, qualities that will shape the future of physics long after individual theories have changed.